So, you are a professor in Nottingham University, specialized in energy and sustainability.
Then people's decisions depend on both deterministic and random responses to stimuli. They are stochastic. The same person may respond differently on different days, even when the underlying stimuli are the same. Our responses also vary between individuals. We want models that embrace this randomness in a way which enables us to make meaningful predictions. So I'm interested in predicting the probability with which firms and individuals are going to invest in measures to improve the performance of their homes and workplaces. But I'm also interested in predicting when people are likely to be present, the activities that they're likely to be performing whilst they're present, and the kinds of behaviors they'll conduct depending upon those types of activities. So we use broadly speaking, three modeling tools in my group to predict these stochastic processes. So one is a really simple family of model or type of model, which we express as a Bernoulli process. So that's simply predicting the probability with which a particular state is likely to be observed. So we can, if the indoor temperature happens to be, let's say, 25 degrees, we can determine the probability with which we observe the window to be in its state open. The disadvantage of this is that we're not properly resolving for dynamics of interactions. So we're not properly resolving for the transition events. So when a window transits from being closed to being open or open to being closed. So to handle that, forget the maths. To handle that, we can model the process that we're interested in as a Markov process, which enables us to explicitly resolve these or predict these transitions in state. We've identified 10 aggregates of activity that we're interested in with respect to the prediction of energy use in buildings. So we've got sleep, we've got passive, that means that we're awake, but we're not really doing anything. Audio-visual, we're using IT equipment, we're cooking, etc., etc. And below, so here are the results of a simulation where we've predicted transitions from one activity to another and then predicted the duration for which that activity survives before we transition to the next. And you can see that there's pretty good correspondence. So we can predict the probability with which certain activities will take place. We can assign appliances to households. Well, oh dear. Then we want to predict the use of electrical appliances conditional on the activity being performed. So we can predict the probability with which cookers are likely to be switched on, given that the activity cooking takes place. So does that approach work? Well, here we've got some box plots where we compare simulated with observed energy use on an annual basis for different types of appliance. So the box plots on the left are for cookers, then microwaves, then TVs, and then washing machines. And you can see that the median, which is indicated in red, is pretty close between observation and simulation. So it would seem that our modeling strategy is fairly reliable. But I did mention earlier that us humans are a bit weird, a bit, we really are. So here we've got, again, use of windows. When the temperatures get particularly warm in summer, and this guy predicts or suspects that it's now warmer outside than it is inside, then he closes his window. He actually evolved over a period of time some really clever behaviors. So this is actually a really smart thing to do, and this is a not so smart thing to do. And this is just somebody who's entrenched in habits that he's not going to change for anybody. Okay, so we do need to take into consideration individuality, and that's rather tricky. I mean, we also want to predict people's comfort, right? But the exciting thing, for me at least, I'm weird too, is that we can take into consideration comfort feedbacks from behavioral actions. So here on the X, we've got different types of adaptive, opportunity that have been exercised. So a person's opened a window, W. They've made a small clothing adjustment, small c, or a big clothing adjustment, big C. Or they've changed windows and clothing, or have used a fan, F. And what's interesting about this is that systematically, compared with no action taking place, The median comfort temperature is always higher when we do undertake some kind of adaptive action. That means that we derive some thermal benefit from or perceived thermal benefit from the adaptive action having taken place. Now that might be a real thermal benefit. We've opened a window, the relative air velocity close to our skin has increased, which improves convective heat transport from our body. Or it might be rather more subtle than that. It might be more psychological. The point is that we can take these factors now into consideration if we've got good quality field survey data. We can predict now thermal sensation probability distributions. We can go a step further and predict thermal comfort probability distributions. I was asked to give some thought as to what kinds of things we ought to try to do in that annex. And that meant that I had to really think about where the pitfalls are at the moment, where the strengths are and where the weaknesses are, and what a good model ought to look like. So for me, a good model fits somewhere within that framework, so presence, activities, behaviors, and comfort. It uses one of the kinds of families of model that I showed you earlier. It's parsimonious, and crucially, it uses parameters that are readily available to modelers. And you'd be astonished in the literature the number of models that use parameters that nobody can predict, that nobody has available to them. And the other thing is that we should honestly declare what the models are good for, and perhaps most crucially, what they're not good for. And we're not very honest at doing that as academics. And when we're using models, we should really be using the state of the art. That's often not done. So challenges, we need consistency in experimental design, consistency in modeling and validation methods, models that are calibrated to good quality data, applications that use the right models for the task, and we need to make sure that our efforts are coordinated. That's it. Thank you very much.